to module 5. In fourth module, we have discussed about the stability analysis of the system using RH stability criteria, root locus diagrams, and Bode's plot. So in this module, we are going to study about the stability analysis of system in the frequency domain using Nyquist plots, polar plots, and state model variables. First, I'll start with Nyquist plots, which is also called as polar plots. Generally, the polar plot of a sinusoidal function g of j omega is nothing but a plot of magnitude of g of j omega versus the phase angle of g of j omega on the coordinate as omega is varied from 0 to infinity. So we are going to make a plot of magnitude versus phase with respect to omega, which gives you a plot named as Nyquist plot. So this is the figure which is showing you the plot wherein I have considered a real and an imaginary axis here. Here we are going to vary the frequency omega. With respect to that, we are going to plot the magnitude of the transfer function with respect to the phase value, which is termed as the Nyquist plots. So thus the Nyquist plots or the polar plot is called as the locus of the vectors of magnitude of g of j omega and phase of g of j omega as omega is changed from 0 to infinity. Now here each point on the polar plot of the open loop transfer function represents the terminal point of the vector at a particular value of omega. That is, you can observe here there are a few points here. These are called as the terminal points of the plot with respect to the particular value of the frequency omega. And the projection of g of j omega on the real and imaginary axis are considered to be its real and imaginary components of the plots. And the next point is coming to the polar plots. The main advantage of using this polar plot is that it depicts the frequency response characteristic of a system over the entire frequency range within a single plot. So that is the main advantage of this polar plots. And similarly, the one disadvantage that we can have in this plot is that it does not clearly indicate the contribution of each individual factors of the open loop transfer function for the analysis. Now we will see how the Nyquist plot is constructed using the integral and derivative factors. The polar plot g of j omega for an integral factor is taken as equal to 1 by j of omega, which is a negative imaginary axis, because g of j omega here is taken as 1 by j omega. And now simplifying this by multiplying and dividing by minus j of j omega gives you the value of minus j 1 by omega. So this we are modifying according to the standard requirement. And in the polar plot, g of j omega for integral and derivative factor, it is represented as 1 by omega angle of minus 90 degree. Phase is considered to be minus 90 degree and magnitude is taken as 1 by omega for integral and derivative factors. And the plot for this particular factor is considered like this. It's minus 90 degrees. So from real to imaginary, we are going to consider this angle. And omega is varied from 0 to infinity in this range. So you're going to get a straight arrow like this. And similarly, for a positive imaginary axis, that is for a derivative factor, g of j omega is taken as j of omega. And for this, magnitude is taken as omega and angle is taken as plus 90 degrees. And the plot for this particular factor is, it's plus 90 degree, and this is 0 and this is infinity, and we are going to go from 0 to infinity. So this is the plot that we are going to get for the derivative factor. And similarly for first order factor like Bode plot, the polar plot first order factor is denoted as 1 plus j of omega, and for this the plot is constructed by varying omega as 0, 1, 2, etc. up to infinity. The real value will be always equal to 1. The imaginary value changes as 0, 1, 2 like this. And the polar plot for this particular first order factor, which is of the form j of omega plus 1, is shown here in the plot. So it's omega equal to 0, omega equal to 1. The value goes like this up to infinity. So we are going to get a straight line like this for a first order factor. And similarly for a first order pole, g of j omega is taken as 1 by g of j omega plus 1, and here as usual we will simplify by multiplying and dividing by the opposite factor, conjugate factor, 1 minus j omega and 1 minus j omega, which will give you the value as 1 minus j omega divided by 1 plus omega square, and which you can split as imaginary and real as 1 by 1 plus omega square minus j divided by j omega divided by 1 plus omega square. And for this, if I start varying the omega value from 0 to infinity like this, 0, 0 0.5, 1, 2 and so on, we are going to get the real value as equal to 1, 0 0.8, 1 by 2, 1 by 5 and so on. And the imaginary value 0, 0 0.4, minus 1 by 2, minus 2 by 5, and last value will be obviously infinity, because anything by infinity will give you the value as equal to 0. And for this particular value, the plot you are going to get like this: omega equal to 0, 0.8, 0.1. So some values we are plotting, and we are going to get a plot like this, a curve like this for a first order factor, which is in the denominator, or it is nothing but called as first order pole. Okay, now similarly here the polar plot for first order factor in the denominator, you're going to get like this. The curve will come like this with real, imaginary and phase and magnitude value like this if I change. Now we will take few example and we'll see how we are going to get the polar plots. So here g of s is given as 1 by s into s plus 1. Here I am replacing s with j omega, so that I am going to get g of j omega as 1 divided by j omega into j omega plus 1. Now simplifying this by multiplying and dividing by the corresponding factors, you are going to get an expression like this for g of j omega, which you can rewrite it as equal to minus, divide and multiply by the conjugate value, that is minus omega square minus j omega. The simplified expression for g of j omega is minus omega square minus j omega divided by omega to the 4 plus omega square. Now for this value, you have to separate the real and the imaginary values as minus omega square divided by omega to the power 4 plus omega square minus j into omega divided by omega to the power 4 plus omega square. Okay, now taking omega square common from both the terms, we are going to get a simplified expression for g of j omega as equal to this. Now construct a table by varying the omega value from 0 to infinity. For few values we are determining the value of real and imaginary, that is 0 0.1, 0 0.5, 1, 2, 3 and so on. These are our real values and these are our imaginary values, which we are going to plot it now in the form of a graph. Now start plotting from omega equal to 0. So omega equal to 0.1, omega equal to 0.5, omega equal to 1. This is the value omega equal to 2. Omega equal to 3, omega equal to infinity is 0. So the plot, when you join all these points, you're going to get a plot like this. So this is the polar plot for the given transfer function. Now coming to the Nyquist stability criteria. The Nyquist stability criteria determines the stability of the closed loop system from its open loop frequency response and open loop poles. And this states that the minimum phase closed loop system will be stable if the Nyquist plot of the open loop transfer function does not encircle -1 and j0 points. So this is the condition for stability, which is depicted in the figure here. So -1 0j comes here somewhere. If your polar plot is outside, is not encircling this part, then it is stable. For example, in this second plot, you can observe that it is encircling this point. Then such systems are said to be unstable. You are not supposed to have -1 in your plot. But again, here also you have this -1 and j0 which is encircled. This is also unstable. And this is a Nyquist diagram which is obtained in the MATLAB for the condition which is shown. Okay, this is our axis plot. So here, if I draw a circle like this, it crosses your plot somewhere here, which is called as gain crossover point. And similarly, this is called as your phase crossover point, the point at which it crosses your 0 dB line. Okay, the point at which this circle crosses the plot, that is called as gain crossover frequency. And this is considered to be our gain margin, and this is considered to be our phase margin, which is shown here in the green color. Draw a line like this at the point where it meets this arc, and this angle is considered to be our phase margin. Now coming to the Nyquist chart. So this is another approach which is graphically used to obtain the frequency response characteristics, which is used in order to determine the log magnitude versus phase plot of the Nyquist plots. So here the plot of the logarithmic magnitude is in decibel, and it is plotted against the phase angle for a frequency range of interest. In the manual approach, the log magnitude versus phase plot can easily be constructed by reading the values of the log magnitude and phase angle from the body diagram. So the main advantage of this log magnitude versus phase plot are that relative stability of the closed loop system can be determined quickly, and that the compensation can be easily adopted or worked out for the given system. So let's consider the Nyquist chart for a simple transfer function where g of j omega is taken as 1 by j omega, and its magnitude is 1 by omega, and phase angle is -90 degree as usual. And we are going to get a plot like this by varying omega from 0 to infinity. And this is the Nyquist chart what we are going to get for a simple transfer function 1 divided by j omega t plus 1. And this is the Nyquist chart what we are going to get for a simple transfer function 1 divided by j omega into j omega t plus 1. Now analyzing the relative stability of the system using the Nyquist chart, here the frequency at which this plot crosses -180 degree, it is considered to be your gain margin, and the frequency at which it crosses the 0 dB line is considered to be your phase margin here in this case. So gain margin here, if it is at the lower side, if it is below 0 dB line, it is positive. If the phase margin here, it is positive. If it is with respect to -180 degree, this is the positive phase margin what we are going to get. And coming to the negative phase margin, if your chart is towards your left side, and if you are going to get a crossover frequency here at this point, this value is considered to be negative, and here this value is considered to be a positive. So this is the chart what you are going to get for an unstable system, and this is the chart what we are going to get for a stable system. So these are few examples of the chart, Nyquist chart, wherein we have a plots of magnitude versus phase. This is how it looks. We have the magnitude in dB here and phase angle here. So now let's draw the Nyquist chart of the open loop transfer function and obtain the phase and the gain margin for this example. So here g of s is given as 1 divided by s into s plus 1 into s plus 3. Now convert this into the frequency domain form by replacing s with j omega as usual, and simplify, get an expression in terms of the complex form. So the value that we are going to get for this is 1 divided by minus 4 omega square minus j into omega cube minus 3 omega. Now multiply and divide by the complex conjugate term and further simplify. You will get g of j omega is minus 4 omega square plus j omega cube minus 3 omega divided by minus 16 omega to the power 4 minus omega cube minus 2 omega whole square. And now separate the real and the imaginary terms and try to get the value of magnitude of j omega in decibels and phase in degrees. So these are the set of values what we are getting for omega equal to 0 0.01, 0 0.1, 0 0.5, 1, 2 and 10. Now for this given value, the Nyquist chart is given here, wherein you are plotting your points with respect to phase and magnitude. So this is the chart what we are going to get for different values of omega. So you can observe one point here which is highlighted in red color, that is 0 0.01 is the value of omega 30 and minus 90 degree. Okay. Another point you can find here which is shown in red color here, that is our third point, 0.5 minus 4.4 and minus 125 degree. So this is your next point what you are getting. Your fifth point here, that is at 2 minus 26 180 degrees. One more point we are going to get like this. Now join all these points in the Nyquist chart, you are going to get the Nyquist plot. So this is the Nyquist chart plot what we have got for the example in MATLAB. So this is your phase crossover point where it is crossing 180 degree line. This is your gain crossover point, and this is the gain margin what we are getting from 0 dB to this point, so it is 22 dB positive. And this is the phase margin what you are getting, and it's again positive plus 7 degree. So system is said to be stable. So this is the view of the Nyquist chart what we have got for the above example. So in today's session you have learned about Nyquist plots and polar plots and how to plot these Nyquist and polar diagrams using the Nyquist chart you have learned, and I hope the concepts are clear. So basically these two plots, they help us to analyze the stability of the system in the frequency domain by considering the magnitude versus phase plot by varying the angular frequency omega. So this is what we have learned in today's session. In the next upcoming session, we are going to take up the state model representation of the systems, wherein we will discuss about the state model, state variables, how to construct the state equation for a given system, and how to analyze the systems using the state variable model will be dealt in the next upcoming session. I hope the concepts are clear in today's session. Thank you all for joining the session. Have a nice day.